Hello YouTube, I'm going to prove the oscillatory motion differential equation, which I used in my how long it would take to fall through the earth video. And so I'm going to rewrite it. I wrote KR. I'm just going to change it to KX, but it doesn't have to be f of g. Just a force is equal to negative kx, and k is a constant. So basically, the force, which changes with x, so the farther away x is from the center, so see, like, the higher the value for x, the higher the force trying to pull it back is. So you can imagine a spring. That's actually, it's called simple harmonic motion. That was a really bad spring. If you try pulling a spring, it gets harder and harder to pull it. So that's a perfect example of it, because when you let go, it'll bounce back and forth. And how do you get a trig function from something like this? Remember, it is equal to the thing with cosine. Well, I'm going to show you. So if you know Newton's second law, F equals ma, which equals to negative kx. All right, so a is acceleration, which is the derivative of speed, which is the derivative of x with respect to t. So a is the second derivative. So we can rewrite it as, let's see, we can divide the m and say d squared x dt squared plus k over m, but yeah, k over mx equals 0. So now we have a second order linear differential equation, homogeneous, I think, yeah. So what we're going to do is we're going to assume our answer is some form of e to the rt. All right, I mean, yeah, e to the rt is x, and we don't know what r is. So if we plug that in here, so the second derivative of that, so that would be r squared e to the rt plus k over m e to the rt equals 0. And then you can factor out the e to the rt. And if you know, because e to the rt doesn't, t would have to be negative infinity for anything with e to be 0. So that means r squared plus k over m has to be 0. Because if you take out the factors, this can never equal 0, because anything to the power of 0 is just 1. So it would have to be an infinitely small number. So this has to be equal to 0. So you can kind of just get rid of that. So you solve it. R equals the square root of negative k over m. Oh, the plus or minus square root. Now, since there's a negative in here, that's also equal to the plus or minus I times the square root of k over m. You can see now where the k over m thing came from. So we can, this is r, so we can plug it in back to our x thing. And so if you know, if you don't know, you have, since it's plus and minus, you have to have both values in the solution. So x would be equal to some constant times e to the one of the solutions, so I square root of k over m, plus some other constant times e to the I square root of k over m. Okay, and here's where it gets a little interesting. E to the I something, well, if you know the Taylor series expansion for sine of x, I don't know why I wrote sine of x down here. I am tired, I don't know. So x 2n plus 1 over 2n plus 1 factorial, and then cosine is just even numbers. So, and you know, e to the x is just x to the n over n factorial. So if we plug in ix into here, it's going to be, we're plugging in ix now. Oh, sorry. So x can be anything. So that would be, that would be ix minus, I cubed, which is negative I. So ix cubed over 3 factorial. And then it'd be plus 5. So plus ix to the 5 over 5 factorial. So it'd always be plus, right? So these are all the even numbers. And if you plug in the cosine, yeah, wait a minute. I feel like I'm missing something. Oh, wait a minute. Oh, I was supposed to plug it in e to the ix. So x to the n over n factorial. Plug in ix now, since this is equal to e to the ix, because of the Taylor series, which would be equal to 0, so that'd just be 1 plus ix over 1 squared, so minus x squared over 2, so cubed would be minus x cubed over 3 factorial, and it goes in pairs of 2s, and you can separate it into the even numbers. Yeah, you can separate into, hold on. Oh, that's why it looked weird. All right, so all right, you can separate it into cosine of x plus I sine of x. So basically, e to the ix, this took a long time to explain, is equal, let me rewrite the differential equation solution, to e to the I plus c2 e to the negative I k over m. So e to the x is cosine of x plus I times the sine of x. So if you're adding up constants, it doesn't matter what you call them. You can make new constants out of them, whatever. So we will expand this into c1 times, so we x, oh, I forgot the t's, oh my gosh. So we pretend these are the x's, because these are all real numbers, and this is I. So it'd be c1 times cosine of, and I'm going to call square root of k over m, well, yeah, k over m, cosine of x plus, I sine of square root of k over m times t. Yeah, sorry. Plus, and then a c2 times cosine. The cosine of a negative number is just a number, so because there's the negative here, so cosine square root of k over m times t plus I. The sign would be negative, because if negative's in a sign, then it goes out of the function, so because it's a odd function. So I sine of square root of k over m times t. Okay, now you can distribute these out. So So let's see. So we have x is equal to C1, where are we? So C1 plus C2, we can just make that a new constant. So I'm just going to make that the new C1. So this C1 and this C1 are different. C1 times the cosine. Yeah, actually, that's kind of confusing. I'm going to call it Q cosine of square root of K over MT. And this would be I sine, C1 I sine of this minus C2 I sine, which is just, we can just make those other constants plus, because these two, yeah, because the constants on here could be imaginary, so that would get rid of the i's and stuff. So we're just going to make, I'm going to make this P sine of the square root of K over MT. Okay, and we're adding, again, the constants. It doesn't matter if you add them or whatever. So you can change this actually into since these numbers add and the actual shifts in here add, we now have x of t is equal to, we're going to call this constant a times the cosine of wt plus the phase constant, since we're shifting it and these things get added together. A is the amplitude, w is the square root of k over m, so yeah, so, and the phase constant is just, so that is how the differential equation was solved from, that's how we got a trigonometric function from f equals negative kx. Thank you for watching.